Hi Year 8, this is our second lesson for probability. In this video we're going to look at compound events. So a simple event is where only a single thing occurs, like drawing a red card from a standard deck of cards. A compound event is a combination of two or more simple events. So for example, drawing a card that's either a black or a queen. There's two things there. It can be a black card or it can be a queen. Tossing a coin and a die. Drawing two cards from a standard deck. And we use the following words when we're talking about compound events: and, or, not, at least, and at most. Here's an example. Sarah tosses a coin and a six-sided die. Let's write the sample space. So think about it, the coin can land heads or tails, and the six-sided die can land 1, 2, 3, 4, 5, 6. So altogether there's going to be 12 different outcomes. Can you list them? You need to be systematic. Remember, we've got to put them in curly brackets as well. So there they are. Heads and a 1, heads and a 2, heads and a 3, heads and a 4, heads and a 5, heads and a 6. Tails and a 1, tails and a 2, tails and a 3, tails and a 4, tails and a 5, tails and a 6. Let's find the probability that we throw, or Sarah throws, a head and a 6. There's only one way that that can occur, isn't there? So 1 out of 12. What about heads or a 6? So any of these plus this one. So that's 7 out of 12. Which might cause you to think, if we're asked for heads or a 6, do we include both? And there are actually two types of or in probability. There's an inclusive or, and in that case it's either A or B or both. So we would include heads and a 6. And there's an exclusive or, and in that case it's either A or B, but not both, so we wouldn't include it. Now, if the question doesn't say it exactly, it's going to be an inclusive or, so we would include it. So let's go back to our question. Let's now find the probability that it's a head or a 6, but not both. So in this case, it's going to be 1, 2, 3, 4, 5, plus this one, but not that one. So it'll be 6 out of 12. Let's look at another example. A bag contains 6 red and 4 green counters with numbers as shown. So we can have red 1, red 2, red 3, red 4, red 5, or red 6, and green 1, green 2, green 3, or green 4. One counter is drawn at random. Find the probability that it's a red 3. Well, there's only one way to get a red 3. There it is there. So our probability is going to be 1 out of 10. Find the probability that it's red or it's a 3. So in this case, we can have all of these reds here and this green 3 as well. So how many is that? 6 plus 1 is 7. Find the probability that it's red or a 3, but not both. So we're going to have 1, 2, 3, 4, 5, not counting this one, and this one, so that's 6. Okay, so this is an exclusive or, and this is an inclusive or. Okay, so we've looked at and, or, and not. Let's have a talk about at least and at most. So the phrase at least means that amount or more. So if we say at least 3, that's going to mean 3 or more. The phrase at most means that amount or less. So for example, if I say at most 3, it means 3 or less. So the important thing with both of these is it always includes the amount that's stated. Here's an example. 2 coins are thrown. Write the sample space for the experiment. So we could have 2 heads, head and a tail, tail and a head, or 2 tails. Now what do you think about these two? Are they the same or different? They're different because we've got 2 coins. So imagine we had a 10-cent piece and a 20-cent piece. The head could appear on the 10-cent piece or it could appear on the 20-cent piece. So there are 4 different outcomes. Let's find the probability that we throw 2 heads. There's one way for that to occur out of 4, so the probability is a quarter. What about the probability that they show the same? It could be 2 heads or 2 tails. 2 out of 4 or we could write that as a half. And find the probability that at least one head is thrown. So it could be this one, or this one, or this one. So 3 out of 4. And here's 2 dice. Now there's a number of things we can do with 2 dice, but one thing is to add their totals together. And this is a grid showing all the outcomes for that experiment. This is how we read it. So if I throw 2 ones, the total is 2. If I throw a 1 and a 2, the total is 3. And that's different to throwing a 2 and a 1 because we've got different dice. Altogether there are 36 outcomes. We're not talking about different or unique outcomes, we're just talking about the total. So it's okay that these are duplicated here. Find the probability, if we throw our dice, that the total is 2. There's only one way to get a 2 out of 36. There's our probability. Find the probability that the total is at least 10. So that means 10 or more. So 1, 2, 3, 4, 5, 6 out of 36. Or we could reduce that down to 1/6. Find the probability that the total is at most 5. So that means 5 and below. So all of these here. So let's count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So answer is 10 out of 36. Now 2 events are said to be mutually exclusive if they don't contain any common elements. And a nice way to visualize this is to draw them as sets. So if we've got mutually exclusive events, it means the sets won't overlap. We put the outcomes of the first event in here and the outcomes of the second event in here, and there's no common elements. Here's an example. Suppose our first event is that I toss a coin. Here's the outcomes. The second event is that I toss a 6-sided die. Here are the outcomes. There's no common elements, and so these are mutually exclusive events. Here's another example. An 8-sided die showing the numbers 1 to 8 is tossed. Let A be the event that the number thrown is even. Let B be the event that the number is a 3. Why are A and B mutually exclusive? Why don't they contain a common element? Do you know why? Because the only element in B is a 3, and 3 is not an even number. But when 2 events contain some elements that are common, the events are said to be non-mutually exclusive. Some people will say they are not mutually exclusive, and that's okay. It's the same thing. Now that phrase has become a common expression in our language. It's moved beyond mathematics. People say things like this: making money and doing good in the world are not mutually exclusive. What do you think that means? It means you can make money and do good in the world. Here's an example. A card is drawn from a standard deck. Find the probability that it is an ace or a heart. Now we looked at this example in the previous video. Let's look at it in light of what we've just learned. So here's the sample space for the aces, and here's the sample space for the hearts. Are they mutually exclusive, or do they have a common element? They have a common element, don't they? The ace of hearts appears in both lists, and so the events are not mutually exclusive. And if we use sets to look at it, you can see how we overlap them. So here's all of the aces, here's all of the hearts, and here is the common element, the ace of hearts. Okay, that's it for this video. In our next video, we're going to look at the laws of probability.